Hello. So now we're going to do another exciting problem here. So the question now will be, suppose that we have a circle of radius 3 centered at the center 2 comma 1. At which point or points does the circle intersect the line y equals 1 half x minus 3 over 4? Okay? Okay. So it's always helpful when you're doing a problem like this or it's not always helpful, but sometimes it helps to make, maybe if not an exact graph, a kind of cartoon to see if there will be intersection points or if there is likely to be intersection points, okay? So if I look at, so what I'm going to do here is I'm going to make a small, I don't really want to call it a graph because, well, you'll see what I mean. And this is another thing too. You'll notice that sometimes when I graph things, I'll graph things very precisely, and sometimes I'll graph things with just enough information so that you know that it's going to give insight, but maybe not as much as you would need for to call it a formal graph, okay? So let's do that here. So what I'm noticing here, of course, is that I have here a center of 2, -1. So I go 1, 2, -1. That's the center of my circle. Let's call it C, okay? And it has radius 3. So I would have to go 3 up, 1, 2, 3 here. 3 to the left, 1, 2, 3 here. 3 down, 1, 2, 3 here. And then 3 to the right, 1, 2, 3 here. Right? And you can, it would be very easy for any one of you to give me the coordinates of those points, of course. Okay, that's my circle. Then they're telling me the line y equals 1 half x minus 3/4. This line, I want to recall to you, is in slope-intercept form, where the -3/4 will be my y-intercept, right? So let me put that in here in blue so we can distinguish it. -3/4 is not quite -1, so it's about right here, okay? I'm gonna put the point right next to the line so I don't touch the line so it doesn't mess up the marker. And then it has a slope that's 1 half. So let's say I go up 1 and then 2 to the right. So that'll be about right here, okay? And so if I draw the line connecting those two, okay, you'll see that it'll look something like this, okay? It's a little flatter here, okay? And even though our graph is not 100% accurate, it's accurate enough for us to see right away, aha, there's no way that this line with slope 1 half will not cross here and here. So we know that it makes sense for us to pursue the solution of this problem. Or not to pursue the solution, but for us to be able to say that there will be solutions to solve. Now, if this... Okay, so now, so for example, if instead of it having been this line, let's say that the y-intercept had been -10, it would have been far down here, and we could have seen going up with slope 1 half that it would likely have not touched the circle. And so even if our graph there had been crude, we would have known that there are no solutions. If the y had been too far positive, let's say even if it had been like here at y, if that had been +2, you can see that a line with a positive slope would have completely not intersected with this circle at all. Okay, so that's why I wanted to draw this figure, and that's why I also wanted to emphasize that I drew it just accurate enough to get an idea, but not necessarily a beautiful, perfect graph. Okay, so now let's continue. Actually, and as I look at it now, it's actually quite accurate. Okay, but we'll leave that aside. Okay. Now, in order to solve this algebraically, we need an equation for this circle, and for that, we're gonna bring back to mind the equation of a circle with center HK and radius R. So what we have here is that the equation of a circle with radius R and center HK is this: x minus h squared plus y minus k squared equals r squared. So here, using this center and this radius, I can see that my equation of my circle is going to be x minus 2 squared plus y minus -1 will become +1 squared equals r squared, which will be 9. That'll be my equation of my circle. And then I'm going to have my equation of my line, which is y equals 1/2 x minus 3/4. Okay? Okay. So what we observe here is that in order to solve this problem, we end up needing a system of equations problem. This is a system of equations. It's not a system of linear equations, so some of the nice techniques that are available to us there, like Gaussian elimination and stuff like that, might not work. But, well, they won't work. But we can use substitution. And so what I'm going to do is, I'm going to take this expression in x for y, and I'm going to substitute it in here, and then that's going to allow us to make an equation in only one variable, which we will then solve for that variable, and then we'll use that variable into either one of the equations to get the variable for the y. Of course, in that case, once I'm there, I'm going to use this equation because it's simpler to recover the y from this equation. Okay, now again, just to recharacterize one more time what exactly a system of equations is. A system of equations, whether they be nonlinear or a general system of equations like these, or whether they be linear equations, a system of equations is basically a set of equations which must each be satisfied for a point to be considered a solution. You can tell that if a point makes this equation true, it'll be on the circle. And if a point makes this equation true, and remember, whenever I say a point, I mean an ordered pair x, y, right? If a point makes this equation true, then it's on the line. So indeed, you can see that if a point makes this one true and this one true, then it must be both on the line and on the circle. Okay? Okay. So now, let us begin. So, as I mentioned before, I already have the y solved for here. So I'm going to insert this expression for y in terms of x into the y there. So this will become x minus 2 squared plus 1/2 x minus 3/4 plus 1 squared equals 9. Okay? You can see that my expression for y in terms of x has replaced the y there. So now I ask myself, what is negative 3/4 plus 1? So negative 3/4 plus 1 is equal to negative 3/4 plus 1 over 1. Because I can represent the number 1 as a fraction by setting it as the numerator and 1 as the denominator. I want to add them, so I have to put them over the same denominator. I can see that if I multiply 1 times 4, I will get 4. So I'm going to multiply the top and bottom here by 4. That's going to give me negative 3/4 plus 4/4. And of course, once I have the same denominator, I can just add the numerators. But let me just write it just one more time like this. Negative 3 plus 4 over 4, which will be 1/4. Okay? Positive 1/4. So I can rewrite this equation as x minus 2 squared plus 1/2 x plus 1/4 squared equals 9. Okay? Okay. Now, what we're going to do... Sorry about the minor disturbance. Okay, so now we're going to begin again like this. Okay, so now we have this equation. So now what we're going to do is we're going to expand the whole thing out. Okay, so this one, I'm going to FOIL it out over here. Okay. So if I have x minus 2 squared, what is that? That's nothing but x minus 2 times x minus 2. How do I do that? Well, it's going to be x times x, which will be x squared, x times negative 2, which will be minus 2x, then minus 2 times x, which is minus 2x, okay, and then negative 2 times negative 2, which will become plus 4, and you guys can see that this simplifies to x squared minus 4x plus 4, okay. So this first term expands into x squared minus 4x plus 4, okay? Okay. Then plus, and then whatever this expands into. So let's do that over here. Okay. So 1/2 x plus 1/4 squared will be 1/2 x plus 1/4 times 1/2 x plus 1/4. Okay? Okay. Okay. So now 1/2 x times 1/2 x is 1/4 x squared. Now 1/2 x times 1/4 will become 1/8x, and it's positive. Then this 1/4 times this 1/8x becomes another positive 1/8x, and then this 1/4 times this 1/4 will become plus 1/16, and then these two like terms, the 1/8x plus the 1/8x, becomes 2/8x, or in other words, 1/4x. So then I can replace this with 1/4 x squared plus 1/4 x plus 1/16, and then that equals 2/9. Okay? Okay. Okay, now I'm going to combine x squared plus 1/4 x squared. Okay? So if I have x squared, that means that's the same as 1x squared. Well, 1 plus 1/4 is going to be 5/4. So this will become 5/4 x squared, okay, minus 4x plus 1/4 x. I know that 16 divided by 4 is 4. So this is negative 16/4 x plus 1/4 x will be negative 15/4 x. Okay? By the way, guys, I want you to know that I'm going to show you these calculations in explicit detail in a moment, but I just want to summarize this so I can write it at the top. I'll do those calculations for you on the side so you can be completely convinced, and then I'll proceed with the solution of this equation. Okay? Then I have plus 4 plus 1/16. I know that 4 times 16 is 64. So this would be the same thing as saying 64 divided by 16 plus 1 is 65/16. Equals 9. This is the equation that we're going to have to solve to find the x's that will correspond to the intersection points. Okay, so the calculations I promised you was the coefficient of the x squared, which is 1 plus 1/4. Then I'm going to have negative 4 plus 1/4. And then I'm going to have 4 plus 1/16. Okay? So I'm going to do those in a moment, but first I'm going to copy this equation up top here so that we can have more room. Okay? So now what I want you guys to see is that I'm going to do these calculations here again just to reinforce your calculation with fractions. I know that there might be occasions when you might have to use these techniques in a test situation, or you might not have a calculator. And so again, and also just because, you know, these are tools that I want you guys to lose the ability to calculate with fractions and stuff. Calculating with fractions is very convenient, and it's something that's critically important. Okay, let's do this together. So let's say I have 1 plus 1/4. The first thing is, they're not both fractions, so I want to write the 1 as a fraction. Any whole number I can write as a fraction by setting it as the numerator and 1 as the denominator. Then plus 1/4. Now, these do not have the same common denominator, but I know that I can multiply 1 times 4, and then they will have the common denominator. So I'm going to put in a little space here, and I'm going to multiply by 4/4. Recall that I always have to multiply and the numerator and the denominator by the same number so that I will not affect the value of the fraction, right? Because a fraction like 4/4 having the same numerator and denominator is equal to 1, and therefore 1 times 1 will still be 1. It'll just be closed differently, which will permit us to do the addition. So this is going to be 4 over 4. Why? Because 4 times 1 is 4. 4 times 1 is 4. Plus 1, 4. Once they're over the same denominator, I just add the numerators and keep the denominator. So that's how I got 5 fourths, which was that calculation. Okay? Now the negative 4 plus 1 4. In a similar way as the 1 can be written as a fraction by setting it as the numerator and 1 as the denominator, I can write negative 4 as a fraction by setting it as the numerator and 1 as the denominator. So this can be rewritten as negative 4 over 1. I'm going to leave a space here for the fraction I'm going to need to multiply to get a common denominator, plus 1 4. Okay? Now, one of the things I want you to observe is that you might ask, well, David, you're putting a space here for a fraction that you're going to multiply to get a common denominator. Why don't you put one here? And if you're asking this question in your brain, I want you to know that that is a completely legitimate and correct question to ask. It just happens that in this case, I can see that I can multiply this one by 4, and then I will both have the same. If it had been like something else, like let's say 1/2 plus 1 over 7, then there would be no way I could multiply 2 to get 7, by a whole number at least, and there's no way I could get 7 multiplied by a whole number to get 2, so there I would have to put a space here and a space here to multiply both fractions by a number to get a common denominator, okay? But here, since I'm looking at it and I can see that I only have to multiply this one to get a common denominator, that's why I only put one space. So we know that that number is going to be 4, because as I mentioned, I know I can multiply 4 times 1 to get 4, and that's going to give us the common denominator. 4 times 4 is 16. So I'm going to have negative 16 over 4, because 1 times 4 is 4, plus 1 over 4. I have negative 16 plus 1, that's negative 15 over 4. That's this number here. Finally, the 65 over 16. So again, 4 plus 1 over 16 is equal to, well again, same story. These are not both fractions, so I have to somehow make them into a fraction. So the 4, I can write it as a fraction by setting it as the numerator and 1 as the denominator. Then I'm going to add the 1/16. Okay. I'm going to put a space here, right? Okay. You can already tell. I'm going to multiply the top and bottom here by 16, because 1 times 16 will give me 16, okay? The question now is, what is 4 times 16? I'm going to do that here, okay? 4 times 6 is 24, so I'm going to bring down the 4, carry the 2. 4 times 1 is 4, plus 2 is 6. As you can see, 4 times 16 is 64. So I'm going to have 64 over 16 plus 1 over 16, and that's 65 over 16, as promised, okay? Now, we're going to do one more step before we're able to use a solution technique for this problem, okay? Okay. Okay. So, in our previous discussions, we have noted that what we want to do is we want to set the equation equal to 0 so that we can apply one of our solution techniques. So in this particular case, I think that the most fruitful strategy is that we subtract this to the other side, and then, well, let me see here. Okay, we're going to do that. We're going to do it by completing the square, but it's also possible that we could have used the quadratic formula, and I still haven't decided, but probably I'll show you both, okay? And, well, let's begin. So the first thing I'm going to do is I'm going to subtract the 65 over 16 to the other side, okay? So basically, this is not going to change, so I'm going to bring it down. 5 fourths x squared minus 15 over 4x, and then this is gone. equals 9 minus 65 over 16. So I'm going to do that calculation here like fully explicitly with the whole calculation listed. Same story. The 9 is not a fraction. I need to set it as a fraction. So I'm going to set it as the numerator and 1 as the denominator. 9 over 1 minus 65 over 16. Okay? Now here, I'm going to need to put this over the same denominator. So just as before, I'm just fortunate that I can use 16 for the top and bottom here. Okay? So now, what is 9 times 16? 9 times 16 is going to be, 9 times 6 is 54. So I'm going to bring down the 4, carry the 5. 9 times 1 is 9, plus 5 is 14. Aha, it's 144. So I'm going to have 144 over 16 minus 65 over 16. Now I'm going to perform the subtraction. 144, okay, what's going on here? Okay. 144 minus 16. Can I take 6 away from 4? I cannot. So I'm going to need to borrow from here. This is going to become a 3. Can I take away, and this is going to become a 14. Can I take away 6 from 14? I can, indeed. It'll be 8. You can verify that. You can say, okay, if I add 6 to 8, will I get 14? Okay, let's do that together. 8, 9, 10, 11, 12, 13, 14. I had to add 6 to get to 14. 3 minus 1 is 2. And then I bring down the 1. 128. Wait, what? Oh, I was subtracting 16. I was supposed to subtract 65. I apologize about that, guys. Okay, let's look at that together here. So, by the way, one of the things I want you to notice there is I caught my mistake, and that's one of the reasons why I want you to always do all your steps, but also more importantly, I caught my mistake because I realized 144 minus 65 has to be less than 100 because 65 is bigger than 54, right? So, but we're at the same problem here. So 4 minus 5, we can't do that. So I'm going to borrow from here. This is going to become a 3. This is going to become a 14. 14 minus 5 is 9. 3 minus 6, I can't do that. So I borrow from this 10. This becomes a 13. 13 minus 6 is 7. Okay? So I can tell now that this is going to be 79 over 16. Okay? Let's do that here. So this is 79 over 16. Okay. One of the things I want you all to observe here is that these fractions all have like a 4 in the denominator or a 16 in the denominator, and especially if we want to complete the square, this looks very ugly. Okay, so what I'm going to do is I'm going to multiply the whole equation, the left side and the right side, by 4, so that this will no longer so that these two will not have 4 in the denominator, and then this will be slightly different. But the most important part is I want to make this one look nice. Okay? Okay, let's do that. So if I multiply the left by 4, I'm saying 4 times 5 over 4x squared minus 15 over 4x equals 4 times 79 over 16. Now, if you go through the whole rigmarole, you'll see that this will become 4 times 79, and then you're going to have 4 times 79 divided by 16, which is essentially 4 times 4. One of the terms of the 4 will cancel. Basically, if you have a 4 on the top and a 4 on the bottom, that's 1, right? So we can eliminate that, and then we get basically 79 divided by 4. Okay? In other words, what I'm saying is that usually you say, okay, we're multiplying by 4, so the 4 will cancel with one of the 4s in the bottom, and that's that. But I just wanted to illuminate a little bit more of the reasoning behind that, why that's valid. Well, let me do that explicitly here. Okay, so I'm going to do 4 times 79 over 16. What does this mean? This means 4 times 79 over 1 times 16. Why? Because I replace 4 with 4 over 1, and I multiply. Well, the numerators multiply, and the denominators multiply. The 4 over 1 times 16 will become 1 times 16. But I can rewrite, but 1 times 16 is just 16. But I can rewrite that 16 on the bottom as 4 times 4. And so I get this. Well, now, if I have 4 times 4 over 4 like this, that's the same as 1. So it's as if it's not as if, it is exactly as though I'm multiplying the two fractions, 4 over 4 times 79 over 4, okay? But then 4 over 4 is 1, and so that's when I can just write 79 over 4, okay? Okay. Now here, I'm not going to go into the full rigmarole, but the reason why I emphasize here when I multiply the 4, well, the reason why I put this in parentheses is to emphasize what we mean when we say we're going to multiply one side of the equation by a number. It means we're multiplying the whole thing. So the 4 times this one will leave us with 5x squared, okay? And the 4 times this one will leave us with negative 15x, okay? Okay. And so now we're in business, okay? Because now here, this is a lot cleaner. I'm gonna pull out a 5 here now. So this is gonna become 5, open parentheses, x squared minus 3x equals to 79 over 4, okay? And now I'm in a position to use the completing the square on this equation, okay? So let's do that. So now I want to recall to you how we're going to do the completing the squares. So I want you to call, the reason why I'm going to do it explicitly here without writing the formula first is because I want you guys to remember that you don't have to memorize the formula that I'm going to use. You will have seen me use this before. You'll have seen me write x plus a squared equals to x squared plus 2ax plus a squared, right? And what we're going to do is we're going to say we're going to try to match the x squared plus 2ax with the x squared minus 3x, right? But the key thing I want you guys to remember is that we don't have to memorize this formula. We can always just calculate it when the moment is necessary. I can do x squared, x plus a squared for my unknown number a, and I can just write, well, what is x plus a squared? Well, x plus a squared is just x plus a times x plus a, like this. And then x times x gives us x squared. X times a is plus ax. Then a times x is plus ax again. And then a times a is plus a squared. Okay? And then, of course, I combine these like terms, and I get x squared plus 2ax plus a squared. And so, in other words, I wanted to show this to you explicitly again to remind you that you don't have to memorize the formula I'm using. You can always just derive it when the time is needed. Okay? Okay. So let me get rid of this for a moment. And so again, what I want to do is I want to find a number a such that the x squared plus 2ax matches x squared minus 3x. And let me re-emphasize why we're doing this. What we basically want to do is we want to replace the x squared minus 3x with an expression of x plus a squared minus the a squared. Because if I'm able to do that, then I'll be able to solve the quadratic by square rooting. Okay? So let's do that. Well, so basically, if this is going to equal to that, if x squared plus 2ax in my general formula is going to equal to x squared minus 3x, then I must have 2a equals negative 3. Okay? So I'm going to divide both sides by 2, and I get that my a must equal to negative 3 over 2. Okay? And then, so then I can use this formula. Okay? I can say that, x minus 3 over 2 squared equals to x squared minus 3x, okay? And then plus plus 9 over 4. Okay, how did I do that? Well, I know that the 2 times the a will be negative 3 because that's what I forced it to equal to here, okay? And then I know that negative 3 over 2, when I square it, will become negative 3 over 2 times negative 3 over 2. A negative times a negative will be positive. The 3 in the numerator of the left will equal to the 3 of the numerator on the right. So it'll be 3 times 3 is 9. And the denominators will be 2 times 2, which will be 4. So I get 9 over 4. So that's how I get this. But look at this. We're there now. As complicated as this quadratic looked, we're about to solve it. Because I can rewrite x squared minus 3x as x minus 3 over 2 squared minus 9 over 4. I'm going to subtract this 9 over 4 to this side. So then I come back to my equation over here. I can now go from here to 5, open bracket, x minus 3 over 2 squared minus 9 over 4 equals 79 over 4. Okay? Now I will confess to you that this equation is already, it's still looking terribly ugly, but what I want you also to realize is that they're not as bad as they look. First of all, I want to get this term by itself, so I'm going to divide by 5. Okay? So if I want to divide by 5, the 5 here will go away, and it'll be the same as dividing that side by 5. Okay, so let's do that. So I'm going to divide by 5. So the left-hand side, I'm just going to leave it as x minus 3 over 2 squared minus 9 over 4 equals 79 over 4 divided by 5. So I'm going to do that explicitly over here, okay? So 79 over 4 divided by 5. Now, one of the things I always emphasize to my students whenever I'm showing them a calculation like this is that you want to make explicit that the 79 over 4 was on top already. Because if you, by putting parentheses over it, and by putting parentheses around it, because if you notice, if I not put the parentheses here, then is it 79 divided by 4? Is it 79 over 4 divided by 5? Or is it 79 divided by 4/5? Or is it, you can already see there's a lot of ambiguity there, so you want to avoid that as much as possible. So, but this becomes, I can rewrite the bottom 5 as a fraction, 5 over 1. So this can be rewritten as 79 over 4 divided by 5 over 1, like this. Aha! Now, whenever we divide by a fraction, we multiply by the reciprocal. So this is going to become 79 over 4 times 1 over 5. Because 1 over 5 is the reciprocal of 5 over 1. Now I can multiply. 79 times 1 is 79. And 4 times 5 is 20. Okay? So I can replace this nonsense with 79 over 20. Okay? Okay. Now I'm going to add the 9/4 to the other side. Okay. So I'm going to be left with, on this left hand side, x minus 3 over 2 squared equals, and then this plus that. So I'm going to do that over here. Okay. So 79 over 20 plus 9 over 4. And I'm going to put in my little brace here, right? Because I know I'm going to have to multiply the top and bottom of the right-hand fraction with something so I can get a denominator of 20. Because I know that 4 times 5 is 20, I'm not putting a space for a fraction next to the 79 over 20. But again, as I had mentioned earlier, if there was no way to get from one whole number to the other by multiplying by a multiple, then we would have had to multiply both of them by some whole number, and we would have had to put a space like this for both to add them, okay? Anyway, let's continue now. So we already know that it's going to be 5 because 4 times 5 is 20. So this can be rewritten as 79 over 20 plus 45 over 20. And then here, if I add 79 plus 45, okay, you can see that this is going to be 14. I carry the 1. 1 plus 7 is 8. 9, 10, 11, 12. So it'll be 124. So it's 124 over 20. Let me see, is that right? 80 plus 44. Yes, that's right. Okay. By the way, what I just said out loud was if I have 79 plus 45, I can see it as 80 plus 44 by taking away one of the ones from the 45 to make the 79 80. makes the calculation easier. But I don't want you guys to get used to doing those techniques. I want you to focus on doing it by hand. And but I just wanted to highlight to you that I was not like cheating there. Yeah. So then here I can start simplifying this because it'll make our lives easier. I can divide the top by 4, okay, and the bottom by 4. If I divide 20 by 4, I get 5. And if I divide the top by 4, okay, let's do that together here, okay. 4 goes into 1, it can't. 4 goes into 12 3 times. 3 times 4 is 12. 12 minus 12 is 0. I bring down my 4. 4 goes into 4 once. So it's 31 over 5. Okay, so that's what I have here now. Okay. So now we can get rid of this calculation here. Okay. Now what I'm going to do is I'm going to take the square root of both sides, because that's going to allow us to get the x minus 3/2 by itself. And remember that when I take the square root, I'm always going to take the positive and negative square root, unless for some physical reason I only want the positive. Okay, but in this case, this is a general algebraic equation. We're not worried about those kind of meanings yet, so we're just going to take the square root and we're going to take the positive and negative. So that is to say, I'm going to get x minus 3 over 2 equals plus minus the square root of 31 over 5. Okay? And so now I'm going to add the 3/2 to the other side, right? Plus 3/2, plus 3/2. And finally, we're going to have x equals 3 over 2 plus minus the square root of 31 over 5. And now we're going to do a little bit of like cleanup work over here. So for example, the square root of 31 over 5. Okay, now this is not going to simplify for us at all. It has no factors that are going to be duplicated. It's just not a good situation. But in general, if we have two numbers that are positive, like a divided by b, like the square root of a divided by b, then I can write it as the square root of a divided by the square root of b. Okay? Now again, I'm assuming here that a and b are positive. Here, therefore, I can write this as the square root of 31 divided by the square root of 5. Okay? Now, one of the things that you will often hear talked about is rationalizing your denominator. It's more nice looking and it's more preferred to have a rational number in your denominator. So what I'm going to do is, to do that, I'm going to multiply the top and bottom here by the square root of 5. So this is one of those moments where we have a fraction that equals 1, square root of 5 divided by the square root of 5, and it's in a context where we're not necessarily adding fractions, but we're doing it, where we're not adding fractions, right? But we're doing it to accomplish a different goal. We're trying to make this expression, we're trying to rewrite this expression, the square root of 31 over 5, as a fraction with a whole number on the bottom. Okay, so here the square root of 5 times the square root of 5, that'll be 5. And then on the top, I'm going to have the square root of 31 times the square root of 5. Now, if you have two numbers, a and b like this, so let me write the rule like this, okay? So if I have the square root of a and a is positive, and if I multiply times the square root of b and the b is positive, then I can conclude that it's the square root of a times b, okay? So again, here I'm assuming a and b are positive. So therefore, what I'm saying is that the top there, the square root of 31 times the square root of 5, will become the square root of 31 times 5. So what is 31 times 5? Let's do that together. 5 times 1 is 5. 5 times 3 is 15. So I'm going to get 155. So that is to say that I can rewrite the square root of 31 over 5 as the square root of 155 over 5. So that's going to allow us to rewrite our roots over here as x equals 3 over 2 plus minus the square root of 155 over 5. Okay? And then what I can do, I can, so basically I can then continue simplifying if I want. Well, in this case, we're not simplifying so much as we're trying to write it more cosmetically. So now I can break it up into our two roots. X equals 3 over 2 plus the square root of 155 over 5. and x equals 3 over 2 minus the square root of 155 over 5. Okay? So these are going to be our two solutions. Okay? Okay. So now what we're going to do is we're going to go back to the original context where we set up this equation and we solved it. And that is, we want to find the y values associated with the intersection points between the line and the circle. And I know that by now you guys are probably like, what? I know you guys probably like had totally forgot that we were actually trying to solve the x for these x's, and we got them now. This one will be the x for this point, and the other one, the 3/2 plus, that will be the x for this point. Now we just need the y's. Oh my god. These are so ugly. But anyway, they're actually super pretty, right? I know that all of you believe that these are beautiful, and I hope that you guys have enjoyed that calculation so far. Okay, so let's look at this together and see where we are. Okay. So now we're going to plug in. I'm going to plug them into this equation here. Okay. So I'm going to start off with that first, with the 3/2 plus square root of 155 over 5. So my y associated with that one will be y equals to 1/2 times 3/2 plus square root of 155 over 5 minus 3/4. Okay. Here, this 1/2 is going to distribute. This is going to multiply here and here. Okay. So it's going to be 1 times 3 is 3. 2 times 2 is 4. 1 times square root of 155 is going to be square root of 155. 2 times 5 is 10. And then minus 3/4. It just so happened that this and this go away, and we're left with just the square root of 155 over 10. Okay? So we can now answer one of the intersection points. The x coordinate, 3 over 2 plus the square root of 155 over 5, comma, with y coordinate, square root of 155 over 10. That's one of the intersection points. And then, well, okay, this looks so jumbled up, so I'm going to put it over here so I can write it nice and big. So my intersection points. So my x is going to be 3 over 2 plus the square root of 155 over 5, comma, and then the y coordinate we got there was the square root of 155 over 10. Okay, that's one of my intersection points. My other intersection point, I'm going to plug in my other one. So y equals 1/2 3/2 minus the square root of 155 over 5 minus 3/4. This is going to be 3/4 again minus square root of 155 over 10. Okay, because 1 times 2 square root of 155 is square root of 155. 2 times 5 is 10, and it's negative. Because this is positive, that's negative, and so it'll be negative. 1 times 3 is 3, 2 times 2 is 4, and then minus the 3/4. It turns out again that this one goes away with that one. So we're left with the y coordinate being negative square root of 155 over 10. So then our second intersection point is going to be the 3 over 2 minus the square root of 155 over 5 with y coordinate negative square root of 155 over 10. Okay? So then, if we wanted to, let's say this is A and A prime, then we can say that this is going to be the A prime, and this is going to be my A. Okay? And there we go. I hope you've all enjoyed this example as much as I have. I hope you guys take your time to really understand all the calculations. I want you guys to see how we use completing the square and Well, I look forward to seeing you again with another problem, and I'll see you then. Thank you.